You can do a lot more than that actually. Full stack doesn't stop at the back end. It actually can go way deeper. In this video we're going to talk about those different layers, or at least a few of them, and what it involves to work in those. Hi there! I hear a lot about full stack development being quite popular, especially in the web environment where you're going to have somebody being able to do the front end and the back end. And that's all fine and dandy, except you can do a lot more than that actually. Full stack doesn't stop at the back end. It actually can go way deeper. In this video we're going to talk about those different layers, or at least a few of them, and what it involves to work in those. We'll have a scale on the side of the screen showing you the different levels at which we are talking about now, and to see how deep we are diving into our conversation there. First of all, the front end. The front end is going to be the thing that is in direct contact with the human that is going to be interacting with it. That's going to be the human-machine interface. This layer is going to mostly define how the data is presented to the human and how does the human interact with such data. Usually it comes from in the form of a website, but you're going to have different aspects of defining that website. First of all, you're going to have to define what process is the user following to actually access the data and interact with it. That's going to be more your UX. And you're going to have the UI part of it. That is going to be the way things look and feel on such website. You're going to have, first of all, the UX that is going to define the process that the user go through to access the data and interact with it. And then you're going to have the UI that is going to define the look and feel of such interface. Finally, you're going to need somebody to actually implement that vision from the UI and UX, and that's going to be your traditional front-end developer. We think about front-end development as mostly a web development, but it actually applies to any system. For example, coffee machine is a front end, at least it got a front end. The buttons, the shape of the buttons, the colors of the buttons, those are going to be the UI, but also the functions of the buttons and the data displayed on the screens or the LED blinking, that is going to be your UX. All those data for now magically given to us, and we are giving it somewhere else, and that somewhere else is going to be the backend. The backend also can be cut in many sections and many parts, depending on what type of data you're processing or the amount of it. If you got big data to manage, well, that's an entire job on its own. And if you got some very advanced processing to do on that data, that's another job on its own. Or AI, if you need some AI, that's going to be specific also. All in all, the backend is going to be the part of the software that actually collect, aggregate, store, and even process the data that you got in your application. Such backend software is going to be running most of the time in a web environment on a server that is going to be running Linux, for example. But you're not forced to always have an operating system below you when you're doing a backend. For example, in many IoT applications, your backend is going to be running bare metal on the microcontroller directly, on the hardware directly, and no operating system at all in that case. Speaking of operating system, a layer down from web backend is going to be the operating system itself. The goal of the operating system is to actually allow multiple applications to share the hardware resources available on the server. For example, the network interface that is going to be shared between different applications. The operating system itself is a bare metal application running directly onto the hardware. It takes the hardware on its own. The OS is the only one able to access the hardware, and then it allows some application on top of it to access it at the right time, defined by the logic inside of the scheduler of the operating system. Now, we are used to operating system being Windows or Linux on server side, but on an IoT device, most of the time Windows is way too big, and even the smallest of Linux is certainly going to be way too big. Typically, some microcontrollers are going to have up to 1 megabyte of flash memory. Flash memory in that case being similar to SSD space on a web server. 1 megabyte of flash is not a lot. Even for the smallest of Linux, that's not enough. So for that entire world, you got some specific operating systems that are way lighter. The Linux Foundation, that is doing the Linux operating system, is also developing the Zephyr operating system, for example, specifically targeted to IoT applications. Another operating system that is very popular within the IoT world is going to be FreeRTOS. That operating system, I can only advise you to try it just for fun. It's deceptively simple to use, as it turns out. It's like Come on, come on. I can only advise you to try FreeRTOS for yourself. It's deceptively simple and easy to use. You just start tasks and they run based on the scheduler inside of it. That's all. If you're used to bare metal application, using FreeRTOS is a breeze. If you're not used to doing bare metal application, then I would advise you to start working with that, playing with it. That's actually interesting to be able to directly control the hardware of your system. That's going to be mostly on microcontroller devices. That's going to be a lot easier than directly onto web servers, for example. Now that we've talked about all the software layers, well, we've reached the hardware, and that part also in the web environment, we don't really care about it. We just get a computer, whatever computer, and that's it. But in the IoT world, well, you got a lot more choices. You can design whatever you want. For example, do you want more processing power? Do you want more memory? Do you want more sensors, more IOs? You can design whatever crazy contraption you want. You're going to be confined by the space or the power consumption of the device that you want, or the battery size that you can embed in your device. But you can go crazy with whatever measurement you want, or whatever crazy human interface that you want. In that world, the first step is going to be to actually do a prototype. For example, assembling some Arduino system. But then quite closely, the next step that's going to follow is going to be designing your own PCB to actually assemble all your components onto one proper device. And then you start running into issues of how to make it as small as you want, or how to connect the battery, or have enough plugs all around it to actually be able to recharge it and connect it to whatever other device you want. All those hardware and mechanical constraints that starts appearing that you most of the time never thought about before actually running into them. A lot of fun, as it turns out, to resolve those issues. All that electronic layer is actually fairly simple to understand, and most certainly if you've finished high school, you already got the knowledge that is required regarding electricity to implement that correctly. Apart from some advanced system where you got high frequency stuff and so on, where some new concepts are needed, for most of electronic, what you've learned in high school is perfectly enough. In that PCB design world, you're going to have some software that is going to be needed to design the PCB itself. And in the open source world, you're going to have KiCad that is very popular. In the more professional closed source, you're going to have Altium Designer that is also extremely popular. Either way, the software allows you to actually design your PCB and the way your components are interconnected, and then generating the files for you to produce the PCB yourself or send it to be produced to a company. Astonishingly, it turns out that nowadays building a custom PCB, producing a custom PCB is actually extremely cheap, with some Chinese producers that allow you to get your custom PCB extremely fast and extremely cheap. Once you've got your custom PCB and you've integrated all the sensors that you want in it, the next step to customize even more is going to be to do some chip design. Yes, designing your own electronic component. We are not able, as amateurs or small professionals, we're not able to design our own chip in our backyard or whatever. This is an extremely capital intensive process that only companies like Intel, AMD and such can afford. But there are ways to go around that, and that way is going to be FPGAs, field programmable gate arrays. Technically, those components are just a bunch of transistors, and with a bitstream, which is a software, you can configure them to be connected to each other in a pattern that you define, that pattern defining the function that is being done by the chip. This allows you to technically design whatever crazy component you want for doing some weird processing, some embedded AI, or processing a lot of data, or whatever functions that you might imagine. Another great advantage to those devices is that you can technically software update your hardware. By sending a new bitstream, you can reconfigure the FPGA at the next reboot, and that allows you to deliver some new features, some new hardware features to your products that are already in the fields. After custom chip, then you're a little bit stuck. The next steps are going to be taking a long time to actually design new physics, new chemistry, new quantum physics, and that is the full extent of my knowledge. I will not go deeper into those subjects. So there you have it. We've reached the end of what I consider as the real full stack. I suppose that if you're watching such a video, you certainly already know one or a few of those layers. I can only push you to actually try and play with the next contiguous layers that might be interesting for you, that can only be fun, first of all, and improve your ability to develop in your current layer. And that's it for me. Thanks for watching. Bye! Bye, Billy! Bye!